All right, let's get into it. Today, we're diving deep into one of the most ambitious ideas in all of science, string theory. It's nothing less than a quest for a single theory that could, potentially, explain everything in the entire universe. Just think about that for a second. What if everything we see, all the stars, the galaxies, you, me, wasn't just a random collection of bits and pieces, but part of one grand cosmic symphony?
Well, that absolutely beautiful idea is the very heart of string theory. It's this notion that everything, and I mean everything, from the tiniest electron to the light traveling from a distant galaxy, is just a different note, a different vibration of one fundamental thing.
But before we can really appreciate this incredible cosmic music, we have to understand the problem it's trying to solve. And it's a big one, a huge conflict right at the core of modern physics. See, on one hand, you've got Einstein's masterpiece, General Relativity. It's the king of the big stuff, planets, stars, the whole cosmic dance. It gives us a smooth, predictable universe where gravity is just the elegant bending of space and time. But then, on the other hand, you have quantum mechanics. It's the boss of the incredibly tiny, the weird, jumpy, probabilistic world of atoms and particles. Now, here's the problem. Both of these theories are stunningly successful, but they speak completely different languages. They just don't get along.
So where does this all come to a head? Well, it happens at the most extreme places you can possibly imagine. Think about the crushingly dense center of a black hole, or the very first instant of the Big Bang. At this unbelievably tiny Planck scale, the smooth world of gravity just smashes head-on into the chaotic, uncertain world of quantum physics, and our theories just break.
And this table really shows you why. With general relativity, the math just goes haywire at what we call a singularity, a point of infinite density. It just can't handle it. But when we try to apply the rules of quantum mechanics to gravity, the math explodes into these crazy, nonsensical infinities that we can't get rid of. This problem, called non-renormalizability, is basically the universe's way of screaming at us, nope, your theories are missing something big.
So, faced with this total breakdown, physicists needed a new idea, a really radical one, something that could turn all that mathematical noise into a beautiful, coherent harmony.
And here it is. This is the big leap. String theory says, forget about particles being these tiny little dots. It proposes that if you could zoom into the very, very bottom of reality, you wouldn't find points. You'd find tiny, one-dimensional vibrating loops of energy. You'd find strings.
And when I say tiny, I mean it's a scale that's almost impossible to wrap your head around. The size of these strings is thought to be around the Planck length. To put that in perspective, if you blew up a single atom to be as big as our entire known universe, one of these strings would be about the size of a tree. That's how small we're talking.
Now, this is where the real beauty comes in. All those different particles we see out there, they're not fundamentally different things at all. They're all the exact same kind of string, just vibrating in different ways, like different notes on a guitar. One note gives you an electron. A different note gives you a photon, a particle of light. And this is the big one. Another specific vibration gives you the graviton, the particle that carries the force of gravity. Suddenly, gravity fits into the quantum world.
So how does this fix that whole infinity mess? Well, think about it. Point particles interact at a single infinitely small point, which is where the math breaks. But strings aren't points. They're little loops. So when they interact, they do so over a tiny area. They kind of smear out the interaction. And that little bit of smearing is all it takes to smooth out the mathematics and make those nasty infinities just disappear. It's an incredibly elegant solution.
Okay, so this sounds amazing, right? We've got a theory that unifies particles and forces and solves the infinity problem. But for all this beautiful math to hold together, the theory makes a demand on reality that is, well, it's pretty out there.
Exactly. You knew it was coming, right? An idea this revolutionary has to have a catch. And believe me, it's a doozy.
For the equations of superstring theory to actually work, to be consistent, the universe can't just have the 3 dimensions of space we see plus 1 of time. Nope, it has to have 10 space-time dimensions. So you're probably asking, okay, where are they? Well, the theory has an answer for that, and it's called compactification. The idea is that these 6 extra spatial dimensions are curled up into an incredibly tiny shape at every single point in our familiar space. They're so small we could never, ever see them or move through them. And this isn't just a convenient way to hide them. The actual geometry of these tiny, curled-up dimensions, these incredibly complex shapes called Calabi-Yau manifolds, is literally everything. The specific shape determines how the strings can vibrate, and since the vibrations determine the particles and forces, that means the shape of these hidden dimensions dictates the fundamental laws of our universe. The physics we see is just a shadow of a much richer, hidden geometry. It's a mind-bending thought.
So as physicists dug deeper into this bizarre, multi-dimensional reality, they hit another snag. Instead of finding one single theory, they found several different versions of it. The whole quest for one theory suddenly looked like it was splintering into 5.
Yeah, by the 1980s, we had 5 different mathematically consistent superstring theories. And that was a real problem, right? How can you have a theory of everything if there are 5 different versions of it? It felt like we had found different pieces to some grand cosmic puzzle, but had no idea how they all fit together.
But then, in 1995, everything changed. A physicist named Edward Witten stood up and proposed something stunning. He suggested that these 5 theories weren't different theories at all. They were just 5 different ways of looking at one single, even deeper theory that exists in, get this, 11 dimensions. He called it M-theory. Nobody's totally sure what the M stands for. Some say magic, some say mystery, some say membrane.
Now, M-theory was a huge step forward, creating this incredible unified picture. But in doing so, it also uncovered the theory's biggest challenges and really opened the door for some of its sharpest criticisms.
So remember how the shape of those extra dimensions determines the laws of physics? Well, here's the problem. It turns out there isn't just 1 or 2 possible shapes for them. The math allows for a truly astronomical number of possibilities, something like 10 to the power of 500. This is what's called the string landscape. Each one of those possibilities describes a potential universe with its own unique laws of physics. So, which one is our universe and why? The theory gives us no way to know.
And that leads us to the biggest criticism of all, the one that really gets people arguing. To actually see a string, we need a particle accelerator trillions of times more powerful than anything we could ever dream of building. So with this enormous landscape of possibilities and no way to directly test the theory's core idea, critics ask a really tough question. Is this really science, or is it just a profoundly beautiful mathematical story?
And it's really important to remember, string theory is not the only idea out there. Its main competitor is called loop quantum gravity, and it takes a totally different path. Instead of adding new things like strings and dimensions, it tries to build a theory of gravity by quantizing space and time itself, saying that space is made of tiny, indivisible little chunks. Both of these ideas are brilliant, both have huge challenges, and critically, neither one has any direct experimental proof yet. So this is where we are. We're left with this profound question. String theory is this breathtakingly elegant idea that seems to solve some of the deepest problems in physics. But to accept it, we have to believe in hidden dimensions and a vast landscape of other universes, all while being unable to prove it. Is it the ultimate theory of everything, a true map of reality? Or is it one of the most beautiful, intricate, and compelling mathematical dreams ever imagined? For now, we just don't know.